All right, can everyone see my PowerPoint?
Yeah.
All right, cool. All right, so hey everyone, I'm Reese Boren. My capstone project is called IronFeed. So it essentially is about getting the calories and macros from images or a barcode and making sure it's routed to make sure that we get the most accurate representation that's available. I built the entire system, ran it against two baselines, and to see which one performs better. Overall, I think my system is performing better based on all the scenarios we're going to see me go through. This is going to be the agenda. So we're going to go over the problem, how the systems work, how I tested it, get the results, then give you a demo and time for questions. So the problem statements, most people start tracking their food. They typically quit within a week or two because typing in every meal is not a fun thing to do. AI hasn't quite gotten around to being 100% perfect with this, although it does make it a lot more convenient. There's still a lot of accuracy problems. Models reading a food photo are off about 35% on calories based on research done in 2025. Even the newer models missed just the weight of the food by about 14%, and this was based on some 2026 research. If you ate a 600-calorie lunch and the app says 800, you stop trusting it and then you quit wanting to use it. So I wanted something that knows when it has a verified answer versus a guess, tells you which one it is, and remembers the meals you eat all the time. So motivation, I track my own macronutrients. So this kind of came out of my own personal frustration and annoyance and my own lack of using these apps because it just turned into too much of a chore. The motivation was never my problem. The typing, and primarily the typing, was. The research says the same thing. Time and effort per entry is the #1 reason people quit. And there's good evidence that hooking the model up to a real food database does work. One study did that with a USDA database and cut the error 63% compared to commercial apps. These apps already have tens of millions of users, so fixing and accuracy matters at scale. Background, bigger picture, poor diet is one of the biggest preventable causes of chronic disease, so this is a health problem, not just a fitness app problem. The tech has gone from paper diaries to barcodes to photo recognition to today's AI models. Every step made logging easier, but none of them solved portions and macronutrients. Figuring out what the food is, that part is basically solved. The part that nobody has solved is how much is on the plate and what's actually in it. Here's some related work. Same pattern every time. Connecting to a model database helps, but everyone uses one source and nobody tells the users how much to trust a given answer. Going down this row, NutriBench tested 12 models on about 12,000 meals, but it only used text. There were no images, and this was done in 2024. Diet AI 24 got 63% error cut, but no clean benchmark images, not real phone photos. Diet Delta does well on weight, but it needs a before and after photo of your plate, and there's no database behind it. So nobody combined multiple sources, a trust label on each item, and real meals. So that's essentially what I'm doing here. The approach, the main idea, instead of asking one model to guess everything, we want to look at what the input is and route it to the best evidence available for it. There are 4 levels of evidence: verified official, meaning the actual nutrition label or the chain's official menu data; a corroborated web, meaning multiple separate searches that agree with each other; model estimate, which is just an educated guess; and unresolved, where the system flat out says it can't back this one up. A verified source never gets overwritten by a guess. Every answer comes back with its label, and if nothing checks out, it says unresolved instead of making up a number. So this design, the router figures out what it's looking at, whether it's a barcode, ingredient, restaurant order, photo, repeat meal, or unclear. Then it goes down the levels in order, official source first, and only falls back when it has to. If the portion of the source is shaky, it asks the users a quick question instead of guessing. Implementation, it's Python under the hood. Whatever you type, or here, let me switch to the next slide. Implementation, under the hood, it's Python. Whatever you type or photograph gets cleaned up in the food, the portion, and the context. Then connectors from the real sources label data for barcodes, USDA for ingredients, and the restaurant's own nutrition pages. Meals you log a lot get recognized and reuse a saved preset instead of getting recalculated. The AI model itself is last in line on purpose. It only answers when the better source came up empty. So for the data collection, I used 30 real meals across 5 types, packaged stuff with barcodes, raw ingredients. I weighed myself, chain restaurant orders, photos of home-cooked plates, and some on-purpose hard cases like blurry photos. The right answers came from the USDA database, open food facts for barcodes, and the official nutrition pages of 7 chains, McDonald's, Chick-fil-A, Taco Bell, Starbucks, Panera Bread, Subway, and Chipotle. I checked
Hey,
every...
sorry, but can you please on the video?
Can I do what?
Your video?
Oh, go to my video?
Yes, I'm
Oh,
unable to see your video.
uh, you can't see my
No, no,
PowerPoint
no,
or...
no. No, your video?
Oh, right. Oh, I see what you're talking about right here. This is the IronFeed capstone demo. It runs 5 frozen examples from the research package. It runs it live through the API call through 3 separate paths. For packaged food items, the important thing is it's not supposed to guess. IronFeed uses the barcode path and reads the food label source. For weighted ingredients, the input already has grams. IronFeed turns that into USDA lookup plus deterministic math. For a chain restaurant item, IronFeed routes to the official nutrition source where it can identify the item. For the home-cooked plate, the constrained resolver asked what is on the plate, then it confirms the ingredients, estimates portion sizes, and then uses USDA math. For the ambiguous dish, all right. So that's the demonstration, the demo I put up. So the implementation, it's Python, and then the data collection. So everything I use just pretty much just food. Data analysis. So this is how it turned out. So when it was just used with plain Gemini, which is Gemini 3.1 Flash or something, the accuracy often came out to about 70%. Its cost was obviously going to be the cheapest. Near exact only about 12% of the time. A lot of the time it was off by quite a bit. Coverage, it did have good coverage because it's pretty much just saying whatever. Gemini Plus web search, then the accuracy does go up. It gets it closer a lot more of the time, near exact 37%. Takes longer, and then the cost goes up because web search ends up costing more API. Whereas IronFeed, since it routes through some free things like the USDA food and database, it ends up being cheaper, a little more than plain Gemini itself, but it doesn't often use web search as much, and it gets a near exact about 61% of the time, and its accuracy goes all the way up to about 88% nearly.
You're left with 5 more minutes.
Okay. IronFeed, and then the findings, IronFeed has the highest results. It was within 5% of the true number 61% of the time. Where it wins, so it wins every time where a verified source exists. Barcode 100% of the time. Raw ingredients about 99.8% of the time. Chain restaurants 97.3% of the time. Home cooked plates were bad for all three systems. Everybody was pretty bad at it around 45% of the time because no official source for your own dinner. The verified answers were off only by about 1.4%, and the whole thing cost about a tenth of a cent per meal, which is about 16 times cheaper than the search version. And for the home cooked problem, I started on a fix, which is going to essentially be force the model to list the ingredients first, then compute the math from the USDA data. That took the home cooked from 41% to about 76%, so it really helps it out. And then for the conclusion, routing to verified sources beats both baselines. The win came back exactly where verified data exists. Home cooked is still hard for everybody, and my little solution I've been working on helps provide a solution to that and make it go from 41 to 70%, 76% accuracy. The takeaway isn't that I needed a bigger model, is that telling the user where the number came from is worth more than the raw model size. For future work, put the ingredients first fix into the thing, grow the test set past 100 cases per category, and run an actual user study. Compare against other top models that are out there like 5.5 GPT and Claude Opus 4.8, and now I guess Fable. Conclusions. Oh, wait. We already did conclusions. Oh, yeah, we already did the demo. These were my references, and I have time for questions.
Thank you for the presentation. So you mentioned comparing against future frontier models. What evaluation criteria would you use to ensure a fair comparison between your approach and your LLMs?
So can you repeat that last part?
So what evaluation criteria would you use to ensure a fair comparison between your approach and newer LLMs?
It would probably be essentially setting up using the existing data that I got from this pipeline and then stacking it up against and the same criteria, just changing the model's API to run that and then seeing what the accuracies come out to be on that.